Independent events are when you have two events to where one does not in any way affect the other. Okay, so it's defined as one event occurring does not affect the probability of a second event. Occurring. So you might wonder, well, isn't that all the time? Like, how do events affect each other? The best example that I can come up with is a deck of cards. Okay? How many cards are in a deck? 52. Okay, 52. So if I were to draw a card, what's the probability I get an ace of spades? 1 out of 52. Now, if I take that card and I keep it out, how many are left in the deck? 51. So if I were to ask what's the probability of now drawing a king of spades, what would it be? 1 out of 51. So did drawing this card affect the next one? Yeah. So that would mean they are dependent events. Independent would be if I were to draw my first ace of spades, put the card back, so restoring it to its 52, and then ask another probability question. Okay, that's the main difference between dependent and independent. So independent, your first thing does not affect the second thing. Dependent is when the first thing affects the second. Does that make sense? Okay. So we do have what's called a test for independence. You're going to have to know this test. Because we don't always get nice examples like a deck of cards where we can visualize and actually think about whether or not it's independent. Sometimes this stuff is just thrown at us in a Venn diagram, and it's, are they independent, yes or no? It's not as easy as mutually exclusive to look at a Venn diagram and go, oh, they cross, so they're not mutually exclusive. Independence isn't that easy to tell. So our test for independence says that the probability of A and B, so that would be the intersection. So if we were to find the probability of the intersection, that it will equal the probability of A by itself times the probability of B. If that statement is true, they're independent. If it's not true, they're dependent, meaning the first event affected the second. Now, when we do OR statements, okay, so our test for independence uses the AND statement rule. Our OR statement, so if we're asked to find the probability of A or B, we would take the probability of A plus the probability of B. So it looks just like mutually exclusive so far, where we just add the two probabilities. The only difference is independent, we have to account for any overlap and double counting. So we have to subtract away the overlap for independent. In mutually exclusive, we didn't have that issue because they never overlapped. If they overlap, you have to subtract that overlap away because you double count it by adding the two probabilities. Yes?
For the top line after the test and the did you say, is it true it's what today?
So if this is true, and we're going to do an example here. If this is true, it's independent. If it's not true, it's not independent. You have like two of those where you're doing the test on your homework tonight. I'll tell you one works, one doesn't, so you'll see how it will look both ways. So really the two things you have to know about independent are these two formulas. So if you know two events are independent, the AND statement, you're just going to multiply individual probabilities. For the OR statements, you're going to add individual probabilities and subtract the intersection. Most of these are going to look like Venn diagrams or tables, and so that's why our examples are a Venn diagram and table. But you do have some that just list them out like this for you, very similar to how we did mutually exclusive. So we're going to do one here where we know they're independent. We're going to find our three probabilities. Then we're going to practice our test for independence. That's what we'll do here on number 2. And then we'll look at the Venn diagram and tables and how we can do our probabilities from those. So first, number 1 is telling us that our events are independent, and it's giving us the individual probabilities of C and D. So how can we find the probability of C or D? Using this formula right here, we'll take our probability of C plus the probability of D minus the probability of C and D. Do we know what the probability of C and D is? Yeah. We do? I know C, I know D. Do we know that one? No. Can we find it though? Because how do we find the probability of the AND statement? We just multiply them together. So this will be the probability of C times the probability of D. So when we start plugging things in, we'll have 0.55 for our probability of C, plus the probability of D, 0.4, minus 0.55 times 0.4. And then you type this into your calculator. Again, you can leave them as decimals since they're in decimals. You don't have to go to fractions. And we get 0.73. So that would be your probability of events C or D. Okay, anyone remember how we did the not C or D? We do 1 minus the probability of C or D. That part is not any different than yesterday. So 1 minus 0.73 will give us 0.27. And lastly, what's our probability of C and D? We actually kind of already did that for the first one. They're not mutually, we don't know if they're mutually exclusive or not, so we can't make that assumption. When we know they're independent, we just multiply the two probabilities together. So we're going to do 0.55 times 0.4, and you get 0.22 as the probability of both. So one of the common mistakes that we make is we confuse mutually exclusive properties and rules with independent rules. So make sure you're reading directions carefully. We can't say an AND statement is 0 unless we know it's mutually exclusive. Okay? Any questions so far? Okay, so then number 2, we're going to practice our test for independence. Here it tells us the probability of E, it tells us the probability of F, and it tells us the probability of E and F together. So our test for independence says that the probability of E and F together should equal the probability of E times the probability of F. So what we're going to do is plug in our numbers and see if it's actually true or not. So if we plug in 0.15 for E and F, and here we'll plug in 0.75 times 0.2, and what do we get when we actually multiply these together? We get 0.15. Do these equal each other? So we can say yes, events are independent. What you're going to see in the directions on your homework as well as on your quiz and test is it's going to say justify algebraically. This right here is our algebraic justification. It's showing that the two sides of the equation equal each other. So when it says that, this is what it's asking for. And that's all there is to the test to independence. You're just checking those two things and seeing if they equal. You okay?
I spelled yes wrong.
Spelled what
I
wrong?
spelled yes wrong.
Yes?
I think I was like unconsciously writing. I was like, that's not right.
Yes.
Yesy?
Yeah.
Alright. Okay, so the next one we're going to try to tell again. This is a test for independence. Are they independent? So here we're given the same type of information just in the Venn diagram form. So what would be, so again we're doing the same test, probability of A and B together. Does that equal the probability of A times the probability of B? So in looking at the Venn diagram, what's the probability of A and B together? 30 out of what? 30, 40, 80, yes. Okay, and then next, on the other side, what's the probability of just A? So that's where we look at just the A circle. What's our total there? Nope. That whole circle? 55 out of 80 times, and then what's our probability of B? 40 out of 80. So if we simplify, I'm going to wait and not simplify quite yet. So if I multiply 55 and 40, I'll get 2200 over 6400, right? Yeah. So then if I reduce my fraction here, I can cross off the zeros. What does 22 over 64 reduce to? 11 over 32. Okay, what does 30 over 80 reduce to? 3/8. So does 3/8 equal 11 over 32? So we would say no, events are not independent. Or if you wanted to, you could say events are dependent. Either way you write it, it's the same thing. Okay, any questions on how we do this test for independence given how any questions on how we're given the information to do our test for independence? Because you could be given it like the number 2, or you could be given it in a Venn diagram like number 3. We're okay so far? Analea, what's so important? Let's put your phones away, you two. Hmm? You can put it away and you grab a calculator from up here. And I know you're not on your calculator because you're texting on Alea. Yes, yeah.
On number 2,
Mm-hmm.
how would you know which one to use to like which of the 3?
Which of the formulas?
Yeah.
Because it's asking, are they independent? I'm going to use the test for independence. So if that's what you're trying to figure out, you're going to use that and test. Okay, last example. And this last one is what you're going to be doing a lot of when it comes to independent. Do you guys all know how to read a table? Yes. Okay. So we're just going to practice reading this table real quick. How many cars are there? Okay. How many vans are there? How many white vans are there? 14. Okay. How many silver trucks are there? Okay. How many black vehicles are there?
100. Oh yeah. 80. Sorry.
Okay. How many total vehicles do we have?
200.
Okay. So one of the biggest mistakes people make is they read the table incorrectly. So are there any questions about how to read the table? What? I say that, but I promise someone's going to read this table wrong. Okay. So when we do our probabilities, when we look at letter A, our probability of picking a car or a white vehicle, you want to ask yourself, do those two things overlap? So do car and white overlap in our table?
Yeah.
Okay, so that means they are not mutually exclusive if they overlap. Okay, because that means they share something. So when we do our probability, we're going to use the independence rules for an or. So our probability of car or white. What's the probability of a car? 100 over 200. What's the probability of white? 100 over 200. But what's our probability of a white car?
200.
The 52. So we have to subtract that out because those 52 cars got counted twice. They got counted in our total for car and in our total for white. So we have to subtract 52 so that we're not double counting. So add your numbers. So when you add 100 plus 100 and then minus the 52, you get 148, and I did not leave myself enough room. 148 out of 200, which you can reduce to 37 over 50. Sorry, I did not leave myself enough room for this. Okay, so when you have a row and a column and they cross, you have to remember to go with your independent rules and make sure you subtract out that overlap. Otherwise, you're going to get, your probabilities are going to be way too big. When I added these all together, so 100 plus 100 was 200, and then minus the 52 gave me 148 over 200. Because when we add, we don't change the denominator, we just change the numerator. Okay. So for the next one, car and white. Okay, are those mutually exclusive? Are they mutually exclusive? So when you're looking at a table, what you're looking at is, do they cross?
Yeah.
then that means they're not mutually exclusive. So what is the probability of car and white? 52 over 200. In a table, we don't have to worry about that multiplying piece, because do we know exactly how many are white cars? So we can just say 52 out of 200. And again, you just want to reduce that to 13 out of 50. Okay, what's the probability of a car or a truck? So are those mutually exclusive?
Yeah.
Yes, because they don't ever cross. They're two columns. So that means, unlike this first one where we had to subtract, we don't have to do that. All we have to do is add the probability of a car. So what's our probability of a car? 100 out of 200. Plus our probability of a truck. So that's 168 out of 200. So when we type that in and reduce our fraction, we get 21 out of 50. Okay, this one's not up here, but I'm just going to ask it to see what you guys think. What's the probability of a black vehicle and a white vehicle?
180. 180.
What's the probability of a black vehicle and a white vehicle?
Four times.
0. Okay, why is it 0? Because you want to ask yourself this question first. Are they mutually exclusive?
Yes.
If they're mutually exclusive and you have an and statement, what is it always going to be? 0. So if you have an and statement, because do we ever see black and white cross?
No, there's still a silver car.
We're not doing like the blending of the colors. We're just saying, do we have a, it's saying what's the probability that one car is black and white?
Oh, one car's like both.
Yeah.
Oh, okay.
And we don't have that. Everything here is a solid color.
Yeah.
So make sure you're asking yourself that mutually exclusive question, because that's going to help guide you to whether you have to add or whether you have to add and then subtract, or whether it's just 0 because they don't ever actually cross.
But if you said or, then it would have been one.
Or we could have had, yeah, or we could have done. It was the and that we couldn't have done. Okay, any questions on that part of reading a table for probabilities? Dima, how's your head? You said it was hurting your head.
Yeah. It's like my nose better.
Okay. So these last two are a little different. This line that you see means something. When you see this line, it means given that. The way I like to think of that line in terms of something you might actually be able to relate to, how many of you have ever done like online shopping? Okay. How many of you have ever used a filter on online shopping? That given is your filter. Okay. So we're going to think of it that way. So here, imagine we're on like CarMax or something. This is asking for what's the probability I get a van given that I'm only looking at black vehicles. So what did how I went from 200, what did black vehicles, that filter, What did that narrow down my search to be?
69 to 80.
Okay, we're out of 80 now instead of 200. And how many of those 80 were vans?
16.
16. So when we reduce that, we get 2/5. So whenever you see that line in between two things, it means you're not using your total, you've got a filtered down total. So if we look at E, we want to know the probability that we get a black vehicle given that we're only looking at trucks.
28 out of 60.
Okay, so we go to our total trucks would be 68, and of those trucks, 28 are black. So 28 divided by 68 would give us 7/17. Okay, yeah.
Can you do one of the not ones? Like, what's the probability of not getting a black car or not getting a truck?
Okay, so what's the probability of not black? Did you want to do a given that or just a not black?
Yeah, just that.
Okay. Is this one of the ones on the homework? Or is it a different color?
Yeah, it just looks similar, so
Okay.
I wanted it.
Now if it says not black,
Oh yeah, there's also one that says, it's like a given one too. It says not cars, and then a given, not
okay,
not.
we'll do one like, I'll
Okay.
advance that. Okay, so here we have a probability of not black. So what we would do is, what's our total? We still have our total of 200 here, because we don't have a given. But how many of those vehicles are not black?
120.
120. So we're looking at not this. So how many are of another color?
Oh, okay.
Because we don't want this, we want everything else. So we would say 120 out of 200 and then reduce it.
Okay.
Now if we said probability of not black given not car. So again, we put on the filter that we don't want a car, which means we're only going to have vans and trucks.
But it's also not black.
Well, let's start with, this is our denominator. So how many vans and trucks do we have?
100.
100.
So we're going to add just these two. Now, of those 100 that we filtered down, so the not cars, how many were not black?
1.
So you're going to add up these 4. Because those are my not black and not cars.
56.
And then reduce it. So when you have these ones that say not, it just means it's almost like you're going to black out. So you're crossing off this whole column, and then not car, you're crossing off this whole row. So it's kind of like you're limiting your table to just a smaller version. I wouldn't actually cross them off on your paper though, because that might get really messy. Okay. Any other questions you guys have so far? Because this is what most of your assignment's going to be, is reading tables and reading them probabilities off of the table. Okay.